Comparing simple harmonic motion with uniform. In this session, we will explore the deep connection between two seemingly different types of movement, oscillatory motion and circular motion. We will begin by establishing the relationship between these two systems and then introduce the concept of the reference circle. By projecting the position of an object moving in a circle onto a straight line, specifically a diameter, we can demonstrate a mathematical equivalence between its horizontal position and the displacement seen in simple harmonic motion. We will also compare the velocity and acceleration of both systems to show that they are governed by the same underlying principles. This approach provides a powerful geometric tool for analyzing and understanding periodic behavior in various physical systems. We can find examples of this relationship in many everyday devices. Consider a traditional, non-electric sewing machine. In this mechanism, the operator provides the initial energy by rocking a foot pedal, known as a treadle, back and forth in an oscillatory motion. This rocking action is transferred to a large drive wheel, which converts that back and forth movement into continuous circular motion. As shown in the image, a drive belt then carries this rotation to the rest of the machine, where it is eventually transformed back into the rapid up and down oscillatory motion of the sewing needle. This practical application illustrates how mechanical systems can seamlessly transition between circular and linear periodic paths to perform work. To visualize this connection more clearly, let us look at an experimental setup. Imagine a ball attached to the outer rim of a turntable with a radius represented by the letter A. The turntable rotates at a constant angular speed, which we represent with the Greek letter omega. In this arrangement, the ball itself is undergoing uniform circular motion. Now, if we place a lamp directly above the turntable and a screen below it, the lamp casts a shadow of the ball onto the screen. As the ball travels in its circular path, its shadow moves back and forth along a straight line on the screen. While the ball moves at a constant speed in a circle, the shadow accelerates and decelerates, moving exactly like a particle undergoing simple harmonic motion. To analyze this mathematically, we use a tool called the reference circle. We imagine a particle, labeled P, moving counterclockwise around a circle of radius a with a constant angular speed. We set our starting point at time 0, where the line from the origin to the particle makes an initial angle with the horizontal x-axis. This initial angle is known as the phase constant, denoted by the Greek letter phi. At any later time, the total angle of the particle is equal to the angular speed multiplied by time, plus the initial phase constant. We then look at point Q, which is the projection of the particle onto the x-axis. As P circles around, point Q slides back and forth along the diameter. We can show that the horizontal position, velocity, and acceleration of the rotating particle P are identical to the properties of the oscillating point Q. By using the geometry of a right triangle formed by the origin, the particle P, and its projection Q, we can find the exact position of the shadow at any moment. The horizontal coordinate x as a function of time is equal to the radius a multiplied by the cosine of the total angle, which is omega times t plus phi. This expression is identical to the standard equation for simple harmonic motion. This tells us that the angular speed of the rotating particle in our reference circle is exactly equal to the angular frequency of the resulting oscillation. By viewing simple harmonic motion as a one-dimensional projection of circular motion, we gain a much more intuitive understanding of why the position follows a cosine wave over time. The equivalence between these two motions extends to how they change over time. The radius of our reference circle corresponds to the amplitude of the oscillation. For a particle P moving in a circle, its tangential velocity has a magnitude equal to the angular speed multiplied by the radius. When we look at only the horizontal part of this velocity, we find it equals negative omega times a times the sine of the quantity omega times t plus phi. Similarly, the particle experiences a centripetal acceleration directed toward the center with a magnitude of omega squared times A. The horizontal component of this acceleration is negative omega squared times A times the cosine of the quantity omega times t plus phi. These calculated components for the circular motion match the velocity and acceleration of point Q perfectly. Let us look at a numerical example to see how this works in practice. Suppose a ball rotates in a circle with a radius of 3 meters at a constant angular speed of 8 radians per second. At the start, or time 0, the shadow is at a position of 2 meters and is moving to the right. To find the phase constant, we use the inverse cosine of the position divided by the amplitude. This gives us two possible values, positive or negative 0.841 radians, because the problem states the shadow is moving to the right, which implies a positive velocity. We must choose the negative value for the phase constant. This allows us to write the final position function as x equals 3.00 times the cosine of the quantity 8.00 times t minus 0.841. Continuing with our example, we can now determine the velocity and acceleration of the shadow. By taking the derivative of our position function with respect to time, we find the velocity. This results in negative 24.0 times the sine of the quantity 8.00 times t minus 0.841. To find the acceleration, we take the derivative of the velocity, giving us negative 192 times the cosine of the same angular quantity. To finalize our analysis, we note that the negative phase constant places the ball in the fourth quadrant at the start. This is physically consistent with the shadow being at a positive x position while moving toward the right, confirming our mathematical model matches the physical reality. In summary, we have seen that simple harmonic motion along a straight line is mathematically equivalent to the projection of uniform circular motion along the diameter of a reference circle. Key parameters in one system translate directly to the other. The radius of the reference circle represents the amplitude of the oscillation. The constant angular speed of the rotating particle corresponds to the angular frequency of the oscillating shadow. Finally, the initial angular position of the particle on the circle, known as the phase constant, determines the starting state of the oscillations. This geometric interpretation simplifies the study of periodic motion by allowing us to use the constant properties of circular motion to describe the changing variables of linear oscillation. To conclude, consider these review questions to test your understanding of the reference circle model. First, if the angular speed of the rotating particle is doubled while the radius stays the same, how does this change the period of the motion and its maximum velocity? Think about the inverse relationship between frequency and period, and the direct relationship between angular speed and tangential velocity. Second, why is it necessary to differentiate between the positive and negative results of the inverse cosine function when solving for the phase constant? Consider how the direction of motion at time 0 provides vital information that the position alone cannot tell us. Reflecting on these points will help solidify your grasp of how circular and oscillatory motions are linked.